start with OSPF neighbors in general. If we have router A and router B here, and we turn OSPF on, what's going to happen is router A and router B are going to neighbor up with each other. So on router A's neighbor table, it's going to have router B. Router B's neighbor table will have router A. If I add router C in here, router B is going to neighbor up with router C. Router C is going to neighbor up with router B. Router A is going to continue to be neighbored up with router B and really won't know that C is a neighbor of router B at all, except for the fact that router C is going to be propagating network information that router A will eventually hear. However, that is not part of the neighbor relationship process in OSPF. Well, if we take these routers, instead of having them linked together with two separate point-to-point links, if instead I set up OSPF where I have each of the three routers connected to a layer 2 switch. When I have all three routers connected to a layer 2 switch, something new has to happen here. Now, since router A is on the same network as router B, which is on the same network as router C, what will happen if we follow the same rules that we used for our point-to-point networks is that each one of these routers on this segment are going to have to build a neighbor relationship with all the other routers on the segment. Well, with three routers, that isn't that big of a deal. However, when we add a fourth router, what's going to happen is all of our routers are going to gain one more neighbor. When we add another router, we're going to gain another neighbor for all the routers. And as we add more routers, every time we add a router to these segments, we're going to add another neighbor relationship. The problem that arises here because of that is if router A detects a link down, what it's going to do is it's going to send out an LSA. That LSA that it sends that out to all of its neighbors. Well, when the neighbors receive that LSA, all of the neighbors then send out an LSA to all the neighbors. So what's going to happen here is we have this mess of LSAs being propagated to tell all the routers about one single update. What can happen when we have this setup where we have multiple OSPF routers all connected to the same layer 2 network segment is we can end up with too many LSAs flooding in that environment. So what OSPF has done is come up with a more efficient way to do this. Now, I'll be very clear about this. This is not necessarily a desired way to set up OSPF. There may be situations where this is needed. There may be situations where you go into a network and this is already set up. However, for the most part, OSPF functions much more effectively when our links are point-to-point links instead of having multiple routers connected all to the same broadcast domain. Now, that doesn't mean that you won't see this. I'm just saying it's not necessarily advised. Well, let's take a look at how OSPF actually deals with this. So what we need to do first is we need to determine the router ID for each one of our routers in this network. The router ID is determined by one of three items. The selection process here is either going to choose the configured router ID first. If there's no router ID configured for OSPF, it's going to choose the router ID that is the highest IP address on a loopback interface. So if I don't have a router ID configured and I do have a loopback interface configured, my router ID will become the same as the IP address on that loopback interface. Last, if there's no loopback interface configured, the router is going to choose the highest IP address on any active interface, and that will become the same as the router ID. Now, the router ID here is written in the format of an IP version 4 address. However, it is not an IP address. It is a numerical value representing the identifier of a specific router in an OSPF network. Well, let's take a look at an example of how OSPF will choose its router ID. So here I have a router. It has 4 interfaces on it, F00 through F03. F02 is a link that is not advertised in OSPF. I have a loopback interface configured with 192.168.0.1 and a router ID configured of 1.1.1.1. So when we turn on OSPF for this specific router, the router ID right now is going to be 1.1.1.1. Well, if it was the case that we started off and there was no router ID configured and we have the same setup, the next best router ID the router is going to choose is the loopback interface's IP address. So in this case, the router ID would become 192.168.0.1. If we did not have a loopback interface configured, the next thing OSPF will do is choose a router ID of the highest active interface on the router. In this case, that's going to be the 192.168.10.1 IP address on Fast Ethernet 0/1. So then that would mean 192.168.10.1 would become the router ID for our router here. Well, if F01 didn't exist, what would happen next is OSPF would still choose the highest IP address on any active interface. This time, though, it's going to choose the 172.16.45.1. Even though it's not participating in OSPF at all, the router is still going to choose the highest active IP address on any interface, regardless if it's participating in OSPF or not. If we go back to our network here and take a look at OSPF Neighbors, what we're going to find out is for router A, I have a router ID configured of 1.1.1.1. Router B, up on the top, that maroon router, I have an ID configured of 2.2.2.2. The rest of the routers, I do not have a router ID specifically configured. So then if we take a look and choose the router ID for each one of these routers, router E is going to use the loopback interface. Router C is going to use the IP address configured on F00. Router F is going to use the IP address configured on F00, and router D is going to use the loopback interface. Now that OSPF has its router IDs selected, what OSPF does next is it selects two routers to be the designated router and the backup designated router. And it does this via an election, and the election occurs by choosing the router with the highest router ID, and that highest router ID router becomes the designated router. In this case, that's router F with a router ID of 192.168.255.1. Next, it's going to choose the backup designated router, and the backup designated router is the router with the ID that is the second highest of all of the routers in the broadcast network. In this case, that's router E with 192.168.99.1. What'll happen now is router F and router E are going to neighbor up with all of the other routers in the network, including each other. Router A, B, C, and D are only going to neighbor up with the designated router and the backup designated router. That way, when one of the routers detects a link down and needs to forward an LSA, what'll happen here is if router A detects a link down, let's say F00 goes down, what'll happen is router A will generate an LSA. It's going to send that LSA to its neighbors, which are router E and router F. And then what'll happen is router E and router F are going to send that LSA update to all of its neighbors as well. And by doing that, we're reducing the number of LSA messages substantially that are propagated when a network topology change occurs. So we gain some efficiencies here because 4 of the 6 routers in here only have 2 neighbors, which makes it a much more efficient way to propagate information between our devices. So let's look at a situation then when router F goes down. Router F is our designated router. What if it bursts into flames and goes offline? Well, what'll happen then is OSPF will heal its network, and it's going to re-elect a designated router. Effectively here, the backup designated router will become the designated router. Then OSPF will elect a new backup designated router with the second highest router ID on that network. In this case, it's going to be router D with a router ID of 192.168.8.1. We'll rebuild our neighbor relationships and then continue to pass traffic. When router F comes back online, what's going to happen is that router is going to become a DR other. Now, the DR other router is not a backup designated router. It is not a designated router. It's the other one. So here, in any case, any router that isn't DR or BDR becomes a DR other. When router F comes back online, it does not become the designated router again. A new election does not occur when a router comes online. What will happen is router E here will remain our designated router. Router D will remain our backup designated router until router E goes down or router D goes down, at which time it will re-elect the designated router or backup designated router depending upon what the situation requires. So our three router types here, just to review, are designated router, the highest router ID when OSPF comes online in a broadcast network. The second highest router ID is our backup designated router. And then all the other routers become DR other.